Hello friends, I am Debanjan and today I am going to show you how did I do my first AI project on digit recognition. You can say it as an algorithm because it doesn't quite change with my training, so it's not a true AI. So anyway, let's get started, and we will be doing the theory part at first and then we'll move on to programming in Python. Theory part at first, I will be taking 28 by 28 pixel images, so that will be total 784 pixels in all total, and each pixel will have its own illumination value. I am taking black background and white foreground for the digit images, so each digit where it will be written will have more illumination than the surrounding ones, so I will be using that fact. Now I will be taking one dimension for each of the pixels, so there will be total 784 dimensions as well. Now for the dimensional thing, I will be giving you an intuitive example. It's not quite related, but it's quite intuitive. So let's see the example. Let's take 3 pixels. So that will correspond to 3 dimensional. So that will be intuitive. Now let this pixel correspond to 1. Let this correspond to 2 and this 3. Now each pixel will have its own illumination, and the most the illuminated pixel, the that corresponding number will be its digit. So let this pixel have 1 by 10 illumination. Let these have let's say half, and these have let's say almost full of let's say 0.9. So that this overall number corresponds to 1, but this is visually representative, but we'll see how does it work to know the basic principle. Now in 3D, coming to 3D, each pixel corresponds to one dimension. So let this be x-axis, let this be y-axis, and let this be z-axis. So here x, y, and z. So let's say this is 0.9. This is 1 mark. I am marking that. This is 1 mark and this is 1. So 0.1 for 2, that will be like somewhere here. Let's say 0.1, and this has 0.5. 0.5. So like this. Okay. So this resulting vector will somewhere be here. Let's say here, somewhere here. So you can see that magnitude is not 1. So we'll make the magnitude 1. Let's say this vector is r. So we are taking that magnitude, and for the 1 magnitude, let's consider that r vector. So r equal to r by magnitude of r. So the direction remains and magnitude gets 1. So we are normalizing basically, and then we are taking a octant of the sphere of unit unit length, unit radius, sorry. So let's draw a fair picture again. Now we are taking an octant of the unit sphere. So, and let's say our r vector is somewhere here, like this. So this is our r vector, and this is 1 corresponds to 1, this corresponds to 3, and this corresponds to 2. So the more closer the r vector to any digit, that will be the digit shown. So here the r vector is more close to 1, so the corresponding digit will be 1. This concept we'll be using in the 784 dimensional space. But how do we know? How do we actually know which is closer to which digit? Like which test image will be closer to which training data? So for that, we will be taking dot product. If you take dot product of this r vector to 1, that dot product will be the greatest. If you take dot product with this 3 and this 2, actually with the x-axis, z-axis and y-axis I, j, k unit vectors. If you take dot products with them, then the dot product will be greatest for the x-axis. So that's how we know that the digit corresponds to 1. So for that we'll be giving training images to the Python program, and we'll be using PIL library in Python to process the image. We'll be taking the each of the pixels illumination value and we'll be storing that as a list. So that will be acting as a vector. This has 784 terms. Now that will be considered as a vector in 784 dimensional space. Now we will be taking a test image and taking dot product of the test images corresponding list. Test images corresponding list will also have 784 terms, and the dot product will be, say, dot product is d, so summation of this as I and this is j, so ij for I equal to j equal to from say 0th term to 784th term. So this will be the dot product. You know, dot product I have written in short form basically. So that will be the corresponding thing. Now we parse the images. We take 3 images for 1 digit in the training. Like for 0, we are taking 3 training images, each corresponding to different writing styles like this, say this and this, like this, and 1, say we are taking standard 1, then some italics, then some like this and this thing. Like this we will be storing the training data. Training data is basically the illumination of the pixels in a CSV file for each of the 10 digits. Now we will be calculating the dot products with each of the digits with each of the training images. So for 0 there are 3 dot products available. We will be summing them up, and now at the last the sum of the greatest digit will be shown. That is the greatest sum which corresponds to a digit, that digit will be shown. So let's start with the programming part, and I have already created digitidentify.py. Let's not waste any more time writing all that stuff again. So I'll be explaining all the functions in detail. So I have imported the PIL library here, and this is the only library I will be using. So let's start. Now this is our first function, image to list. This basically does that we are going to take an image path which I will be giving from here training folder. I have stored all the training data. I'll be showing that, and also I have created some test images which I'll be testing with. So this takes an image path and parses the image into its pixel illumination values and converts that into a list, parses that pixel illumination value from here and converts that into list, which list name is pixels, and returns that list, return pixels. Now we will be giving input of image path and corresponding digit for training that model. But before that, we need to add to CSV. So while training, we will be taking the corresponding digit and as well as the image path for that digit. So I am opening a CSV file called training data.csv. You can see here. Now I will be explaining that in a while. Pixels equal to image to list. I am creating just a list of that list of the parsed training image into a 784 termed vector, which is a basically list contained in pixel name. So and then it adds to CSV. Basically it adds a comma and then another pixel value, and then adds a comma and another pixel value, like that's it. So we will be using the add to CSV function for training data.csv. Here I am showing the training data. I will be taking 3 sample of each digit for training. The first one, the first element actually shows which digit it is. 0 0 0 1 1 1. These are all in ascending order. Now I have given a training data previously. Actually, I have given the training path from here. You can see training inside training folder. I have several images. This is the sample of 0 I have given. So this training means 0_1. That means that 0 is the digit and it is the first sample. 0 is the digit and it is the second sample. Second sample is this and third sample is this, like that. I am showing you some random images from here. This is the sample of 2, second sample of 2, third sample of 2, sample of 4, sample of 8, and all these are here. So I have already stored the pixel illumination values here. So this contains all the 784 terms of the pixel illumination. Basically that's it. So in a moment I will be showing you the train.py, but before that we have to know the dot product function. I have created a dot product function to take input of two vectors v1 and v2. Vectors are here, the list of 784 elements of each image containing the pixel illumination values. So I am taking input of that and then I am just returning the sum of I into j for I comma j in zip v1 v2. Zip function is used for returning a tuple for first position of each of the first, not first, but ith and jth position for each of the v1 and v2. Basically does the dot product actually. Now I have defined a dot product list which takes image path, but before that I will be showing you the training.py. So let's see the training.py. With training.py I am just storing the training data in train data.csv. That's it. And we are taking the digit so that I can store the digit as the first element of the CSV line. And then we are taking the image path from I have actually created an ideal image for each of the digits, which will be the first image, and then image path variation 1 and variation 2. From here you can see the training data. 0.1 is the ideal, 0_1 is the ideal, and 0_2 and 0_3 are the variations of the digit. So I will be giving all the paths by copying from here while running this program. And we are done with the training.py, and thus we have stored the training data.csv. I am showing just one example. We will delete that line later because I have already stored that. So let's do it. Digit will be, say, I am giving 1 and then from training, and now I have copied the path, and by left clicking by right clicking I will be entering that path here. Copy path. Imagine variation 1, variation 2 will be like this, and then it will automatically parse the image and store that in the CSV file. That's it. I'm keyboard interrupting here. So I have already actually trained that model, so I am not going to disturb it. I'm going to delete the last line because I have already trained it. Now our next function is dot product list. It takes an image path from the user, and this function is basically used while we run the program for testing. I will be using this test data which I have created, like this one and then this one, this 3. You can create also something like that with Microsoft Paint. You can create. I have created with Krita, doesn't matter anything. Krita is free also, so you can use that also. Now we will see the dot product list. It takes image path, and that image path is for test image. Remember that pixels stores the parsed pixel illumination values from that test image data, and then we create a empty list dot products. Here we will be storing the dot products of the test image data with the train data.csv's each line. So there will be 30 elements in the dot product list, and before that dot product list is created, actually we use a for loop, and then we are normalizing that data, because if we don't normalize, say for 8 there are many pixel values which are white, so that will be uh, that vector will be most in the magnitude, and all the uh, test data will show that the digit is 8. So I have already told that also in theory. So we are normalizing, basically we are doing that little r equal to uh, big R by magnitude of R, so that does the magnitude as 1 and preserves the direction, and that's it. And we then append the dot product in dot product list, and then we return the dot product list. Now the dot product list contains 30 elements, which are like dot product for sample 1 of 0 digit, sample 2 of 0 digit, and sample 3 of 0 digit. So we will be summing that in the testing.py. Now before we do the last function of the digit identify, that is identify digit, we will be seeing the testing.py. So it does basically that, takes the image path of the test image and produces the dot product and stores that in dot product equal to di dot product list. I have imported the digit identifier functions as di, and then it prints the digit is, and then we identify the digit by the function identify underscore digit, which takes input the dot product. So that's it. We'll be seeing the last function of digit identify as of now. Now this is our last function, identify digit. So we take the dot product list which contains 30 elements, the dot product with individual train data dot css lines, and we create a empty list sum dot products which will contain 10 elements, that is summing up 3 after 3 in the dot product list. So we do that. Dot product list contains 3 element each in group for each of the digits. So we sum them up, and then we return the maximum of the sum of dot products. So that's it. Now we will see some testing. Now that we are done with the all the functions and all the Python programs, so let's start testing. Let's see some test results. Say I'm testing 1. I'm copying the path. So this has been identified as 1, which is correct. Let's say another 1. Copy path. Okay. So this has identified as 6. Let's see 2. Copy path. Okay, this is correct. 2. Let's see a 3. Okay, this is 9. This is showing some wrong results. Okay, that will not be actually definite. So this is also expected that it will show some wrong results as well. Okay, this digit is 4. It's correct. Now let's see some other. Let's see this 6. Copy path. And here is 6. Let's clear the screen and do another testing. It's the 7. We should identify 7. Copy path. Okay, this is 7. Let's do another. Say 9. 9 path. Okay, this is 9. Let's do a 5. Okay, this is 1. So another wrong result. This is okay. Okay, this is also 5.